Good morning, everyone. We are presenting the topic demand-side management in smart grid, concepts, challenges, and applications. I will cover the foundations, why demand-side management is important, what DSM means in a smart grid context, how it differs from demand response, and what major DSM types are used in practice. After that, my teammate will discuss flexible and non-flexible loads, enabling technologies, benefits, and challenges. Finally, our third presenter will discuss real case studies and a roadmap for Malaysia. Okay. Let me begin with the main problem. Traditional power systems were operated with the idea that supply must always follow demand. A system operator focused demand dispatch generators and reinforced transmission and distribution network so that the peak can be served. This model worked when demanded was predictable and the most flexibility came from dispatchable fossil fuel generators. However, the energy transition changed this logic. Solar and wind generation are variable and weather dependent. Electrification is of transport, cooling, industry, and the data centers change the daily load sharp. At the same time, consumers are becoming prosumers through rooftop solar batteries, electric vehicles, and smart appliances. Therefore, demand can no longer be treated as only a passive quantity to be served in a smart grid. Demand itself can become an active resource. Okay, this leads to the central thesis of our report and transportation. Uh, Demand side management should be treated as a resource portfolio, not as a single program. DSM is not simply telling customers to use less electricity. It is intelligent management of when, where, and how electricity is consumed, while still preserving useful energy survives. In some cases, DSM avoid unnecessary energy use through energy efficiency. In our cases, it shifts flexible demand away from peak hours and towards low cost or renewable rich periods. In more advanced cases, automation and aggregation allow thousands of small devices to provide greater scale flexibility. So the key idea is not discomfort. The key idea is useful flexibility. Now let us define DSM more precisely. In the smart grid context, a smart grid is a digitally enabled electricity network that can monitor, communicate, and manage generation, network asset, and end-use demand. DSM uses this smart grid capability to influence electricity consumption. A common way to describe this DSM is that it involves planning, implementing, and monitoring actions that influence customer electricity use and change the time pattern or magnitude of load. This includes energy efficiency, traffic design, uh, demand response, direct load control, automated control, distributed energy resource aggregation, and customer engagement. A useful way to understand this DSM is through the load curve. The load curve shows demand over time. Traditional systems are designed around the highest peak because generation capacity, reserve margins, transformers, and cables must be set to serve it. DSM can reduce system stress in three main ways. The first is peak clamping, which reduces demand during high load period. This can happen through direct load control, price response, or automatic demand response. The second is valley filling, which increases useful demand during low load or high renewable periods. This is valuable in solar-rich system where there may be surplus midday generation. The third is load shifting, which moves flexible activities from a constrained period to be a better period without reducing the final energy service. Okay, and the DSM programs can be grouped into several major types. The first type is energy efficiency. This is the most permanent form of DSM because it reduces the energy required to provide the same service. Example include LED lighting, efficient motors, variable speed drives, efficient chiller, and improved building envelopes. In Malaysia's tropical climate, efficient cooling is especially important because air conditioning can strongly affect peak demand. The third type is price-based demand response. This includes time of use tariffs, critical peak pricing, and real-time pricing. Time of use tariffs charge different rate during peak and off-peak periods. Critical peak pricing applies a high price during a small number of stressed hours. Real-time pricing reflects changing market or system conditions. This program preserve customer choice, but their effectiveness depends on whether customer understand the signal and have automation to respond conveniently. And the third type is incentive-based demand response. Instead of exposing customers directly to changing price, the program pay customer or gives bill credit for reduce reductions. Example include event pays, interruptible tariff, and capacable payment. This type is valuable when the system operator needs reliable response during tight system conditions. And finally, DSM can be scaled through aggregations and virtual power plants. A single household device is small, but thousands of devices coordinated by an aggregator can become a market-scale resources. This is a major development in smart grid because it allows distributed demand-side resources to participate in capacity, energy, reserve, or network support services. Okay, I will now pass to the second Fred, 黄百千.
First, let me explain flexible loads. Flexible loads are electrical loads that can be delayed, shifted, reduced, or temporarily interrupted within a certain time period. In simple words, these loads do not need to use electricity immediately. For example, electric vehicle charging is a flexible load. An EV does not always need to charge during peak hours. It can be charged later at night when electricity demand is lower. Another example is air conditioning. During peak hours, the temperature setting can be slightly increased to reduce power consumption for a short time. Battery storage is also flexible because it can charge when demand is low and discharge when demand is high. Flexible loads are important because they help the grid reduce peak demand and operate more efficiently. There are three main reasons why flexible loads are suitable for DSM. The first reason is time flexibility. Some devices only need to complete a task within a certain time window. The second reason is thermal inertia. Some systems, such as air conditioning, can maintain temperature for a short time, even if electricity use is reduced. The third reason is energy storage capability. Batteries can store electricity when demand is low and use it later when the grid is under pressure. Next, let us look at non-flexible loads. Non-flexible loads are electrical loads that must operate continually. They cannot be easily delayed, reduced, or interrupted. For example, hospital life support equipment is a non-flexible load because it is directly related to human life and safety. Another example is traffic lights. They must work continuously to maintain road safety. A third example is coordinate certain services which need constant electricity to keep communication and digital service running. Because these loads are critical, DSM should not control them directly unless they are strict safety protections. In real power systems, there are also partially flexible loads. So these loads cannot be completely turned off, but they can be adjusted within a limited range. For example, commercial lighting can be dimmed in non-critical areas. Office air conditioning can be slightly increase the temperature setting. A date-certain cooling system can optimize cooling, but it cannot fully stop cooling. Therefore, load classification is very important in DSM. Grid operators need to know which loads are flexible, which are not flexible, and which are partially flexible. If flexible loads are managed properly, they can support the grid, but if no flexible loads are controlled incorrectly, they may create safety risks. Now I will move to the second part, The challenges of DSM. Although DSM have many benefits, it is not easy to implement in daily life. The first challenge is low user participation. DSM depends on whether consumers are willing to change their electricity use habits. If users do not understand the benefits, or if the reward is too small, they may not want to participate. The second challenge is data privacy. DSM relies on smart meters and detailed electricity data. This data may show users' daily habits, such as when they are at home or when they use applications. So users may worry that their private information could be misused. The third challenge is cybersecurity. DSM uses digital communication and remote control. If the system is attacked, hackers may steal data or disturb grid operation. Therefore, cybersecurity is very important. The fourth challenge is the rebound effect. This happens when users reduce electricity use during a DSM event, but they restart their device at the same time after the event ends. This may create a new demand peak. The fifth challenge is technology and interoperability. DSM involves many devices such as smart meters, smart appliances, and EV chargers. If these devices use different communication standards, it becomes difficult for them to work together. The final challenge is market and policy barriers. DSM needs clear rules for measurement, payment, data ownership, and market participation. If the rules are unclear, users and companies may not have enough motivation to join DSM programs.
Hello everyone, my name is Zanzhong Nan. In my part, I will focus on 2 real case studies so we can understand how DSM is actually used in the power grid. First, I will talk about the Malaysia case, which is the TNB time of use and enhanced time of use tariff. This is a typical example of price-based DSM. The basic idea is simple. Electricity price is not the same for the whole day. During peak hours, the tariff is higher. During off-peak hours, the tariff is lower. So, customers are encouraged to move some electricity use away from peak time. For example, TNB's time of use scheme gives lower tariff rates during off-peak period. The off-peak tariff rider also gives a 20% discount on electricity usage during off-peak hours, from 10 p.m. to 8 a.m. This means customers can save money if they can shift some loads to the nighttime. The enhanced time of use tariff is a more detailed version. It has 3 different energy rates: peak, mid-peak, and off-peak. It also has 2 different demand charges, peak and mid-peak. Here, energy rate means the charge for how much electricity is used in kWh. Demand charge means the charge for the highest power demand in kW. So ETOU encourages customers not only to reduce total peak energy use, but also to avoid very high power demand during peak periods. From the DSM point of view, this case works in 4 steps. First, TNB sets different tariff rates for different time periods. Peak time has higher electricity price, while mid-peak and off-peak periods have lower prices. Second, customers identify flexible loads. These may include cooling systems, pumping systems, some industrial processes, EV charging, and battery charging. Third, customers shift part of these loads from peak period to mid-peak or off-peak period. Finally, DSM benefits are created. Customer electricity bills may decrease, peak demand is reduced, and the overall load curve becomes smoother. This case connects very well with DSM concepts. It is price-based DSM because customers are guided by price signals. It also shows load shifting because electricity use is moved from peak to lower price periods. It supports peak clipping because peak demand and maximum demand can be reduced. It also supports valley filling because off-peak electricity use is encouraged. Most importantly, customers are not passive users anymore. They become active participants in grid operation. Next, I will move to the second case, the UK Demand Flexibility Service, or DFS. This case is different from TNB, TOU, TOU. DFS is not based on a fixed time of use tariff. Instead, it is an event-based and incentive-based demand response program. It rewards households and businesses for changing electricity use when the power system needs support. The process of DFS is also quite clear. First, NESO identifies a tight system margin, which means the grid may face high demand or limited supply. Second, a DFS event is sent to customers through electricity providers, usually by app, SMS, or email. Third, users reduce or shift flexible loads during the event period. Fourth, smart meter data is used to check how much electricity has been reduced. Finally, rewards are paid and peak stress on the grid is reduced. A simple household example can help explain this. Suppose there is a DFS event on Monday from 5 p.m. to 6 p.m. A family originally planned to cook, use the washing machine, and charge an EV during this hour. During the DFS event, they keep only essential electricity use. They delay the washing machine to 8 p.m. and charge the EV later at night. As a result, the household may save about 1 kilowatt hour during the event. One household's reduction is small, but if many households and businesses do this together, the total reduction becomes useful for the grid. The real result also shows this. In the winter of 2022-23, around 1.6 million households and businesses participated in DFS. There were 22 events, and more than 3,300 megawatt hours of peak time electricity reduction was delivered. This shows that customer-side flexibility can become a real grid resource. The key difference between the two cases is this. TNB TOU tells users when electricity is cheaper, so users can plan their consumption in the long term. UKDF asks users to reduce or shift electricity use when the grid is stressed, and then rewards them after a successful response. So, TNB is mainly price-based DSM, while DFS is incentive-based demand response. To conclude, these two cases show that DSM can be implemented in different ways. Malaysia's TNB2U ATOU uses tariff design to guide customer behavior. The UK DFS uses event signals and rewards to get short-term demand reduction. Both cases show the same important idea. In a smart grid, customers are not only electricity consumers, they can also become flexible resources that help reduce peak demand, improve grid reliability, and support future energy transition. Thank you. That is the end of our presentation.